This meeting is being recorded.
So back to class and recapping. This is Wildcard week, and this is the last week of a new technical topic. So to understand Wildcard week, every year at the end of the Fab Academy, we step back to review what we covered, what worked, what didn't, how to improve it. And there's always a question of, can you add X, where X is a topic somebody would like to see. And we come back with, well, if you want to add that topic, what would you remove? But there's no topic here that anybody would like to remove. And so the way we started handling that is with Wildcard week. Until now, everybody's done the same assignment, and we make sure everybody has the same tools. In Wildcard week, it's the opposite of both. So this is a week where you can use whatever specialized tools your lab have that aren't standard, and you can do an assignment that's different from anybody else. So you're going to make the assignment, not us. So let me start with what is the assignment. So I want you to design and produce something. It has to be a digital process. And what I mean from that is there's a computer involved in the design and in manufacturing, as opposed to just manual skills. I celebrate manual skills, but that's not what this assignment is about. This has to involve a computer in designing and producing. Then here's the key distinction. It has to be something we haven't covered in another assignment. So it can't just be doing a better job of something we already covered. It has to introduce a new skill. You have to clearly identify what's the skill. Then you document not just what you did, but document the assignment. What is the assignment that you're doing? And then cover everything needed to produce it. And so in the past, this week was just composites. Let's see. Tom is asking about computer vision, and Tom, the answer to that's yes. I'm going to come to that. In the past, this week's assignment was just composites. I have linked to an example here. I'm going to spend about half of class today talking about composites. And so previously, everybody just did the composites assignment, and you could do that. But I'm going to spend the first half of class giving you a tour of many other options that would be fine for this week. So first we'll do breadth with many options, and then I'll drill down into composites. So first one is multi-axis machining. This is a 5-axis machine tool in my shop at MIT. So it moves in 3 axes, X, Y, Z, and then it can rotate and rock. That's about $100,000 tool. You can do that. This is an $800 3-axis mill where you can add a 4th axis. And in fact, for multi-axis machining, in molding and casting, if you printed a mold, you could use this week to do full 3-axis machining. So if you've only been doing 2-axis machining, you can use this to do 3-axis machining. But what I mean by that is a toolpath that's moving Z while moving X or Y at the same time. And if you have access to, you could use this to work on 4-axis machining where you rotate while you machine, or if you have access, going up to full 5-axis machining. And so there's all sorts of things you can machine in materials that are hard to print to do multi-axis machining to make more complex geometries with beautiful surface finish. So that would be fine for this week. EDM, this is an EDM in my shop. If you have access to that, it's a wire, and then a plasma is produced around that wire, and that eats away at metal, and that lets you make metal parts with high aspect ratios with beautiful surface finish. This is a water jet cutter. Again, that's about $100,000 tool. Not Waver, Wazer. Wazer is about a $10,000 smaller tabletop version. The water jet cutter cuts with a supersonic jet of water in training a garnet abrasive that machines ballistically. And the great attraction of that is you can cut material you can't machine. So glass, stone, ceramic, all sorts of materials that aren't machinable, you can cut with the water jet. That would be fine. This is a Zun cutter. Again, about $100,000 tool. It's like a giant vinyl cutter, but a big difference from a little tabletop vinyl cutter is there are many degrees of freedom in the head. So you can vibrate, you can rotate, you can angle, you can punch. There's many more operations than just dragging a knife. And so learning to program a large format flatbed cutter is an interesting thing you can do this week. Water jets consume a lot of garnet. Plasma cutters, you use a plasma generator to make a torch that melts metal. So this is only for metal, but it lets you do large format metal cutting with a plasma torch. Originally, those were pretty messy. There's a lot of slag. It's still hazardous, dangerous. You need it in a workspace where you can shoot out a plasma jet, but the quality of the cuts has gotten much better, so they're much cleaner. Much higher power lasers can cut metal. This is a fiber laser that can do laser metal cutting. And then this is another kind of laser in my lab that does micro machining and lets you make micron scale parts with a very different workflow. So all of these would be fine for this week as more advanced kinds of machining. Welding is a universe of, you can do it with oxyacetylene, MIG, TIG, or all types of welding. And the welding itself, it can be automated, but welding is acceptable for this week if you start with a metal cutting process and then you use welding for the joining. We all did molding and casting. We didn't do vacuum forming because it's less universal. But so what this was, many of your labs have a vacuum former. This is a project where the student made their own vacuum former, but it shows the process nicely. So you heat a plastic that softens. You then pull a vacuum that pulls the plastic around your part. And then when it's done, you get a faithful reproduction of your part. And so this example, which included making the vacuum former, was used to make a form to make custom soap. So that's vacuum casting. And then again, this was another project where actually making the machine was a final project. And I'd showed this in molding and casting, but if you have it, you could do that this week. Roto casting is where you tumble the mold to cover the inside surface of the mold. So those are some kinds of molding and casting. Then an interesting thing you could do this week is fold. Eric Demain is a colleague at MIT who's known for taking origami and turning it into a rigorous subject. And let's see, his site doesn't seem to be loading. I'll send him a note to him about that. But this is just on the background of the mathematics of folding. And he's, oh, let's see, is it a network issue? No. Not sure what was happening there. But this was a student thesis in my lab on cutting and folding. So he developed really interesting processes to take a 2D design, to take a 3D design and turn it into a 2D cut pattern you can fold to make the 3D shape. And he also developed machines to automate the folding. And then he went on to show that you can, by varying the cut pattern, you can vary the mechanical properties. So you can, in effect, have a single sheet stock, but tune it as if it's a wide range of, so this is a range of elastomers, and here he has a single material. This is the stress versus strain. And he's showing that he can match the range of those properties just by how he folds it. And then this was work that followed that from one of my students on kirigami, which is origami with cuts as well as folds. And he's doing metal folding. And in it, in the linked paper, he shows how to design these high strength folded structures by cutting and folding in metal, which you can do in other materials. And a really neat thing he did was let's see, I think the easiest way I can find that is here. Using those techniques, he did a large format art installation where these were made by cutting and folding. This is an aluminum polymer laminate cut on a large format flatbed cutter. And each of these in hours went from sheet stock to these folded structures. So folding, and in particular folding to make 3D forms and tuning mechanical properties, is something you can do this week. For robotics, these are robotic arms in my lab. Something you can do is program the arms themselves to do things like automating assembly. You can put end effectors on them. Colleagues at ETH in Zurich are masters of programming robots to do building construction. So these are just examples of work in their lab of programming robots to construct. And then soft robotics is Adriana, one of the gurus, has this nice tour through molding and casting elastomers to make robots that you deform pneumatically. And you can make all sorts of mechanisms, locomotions, robotic behavior. A colleague at Harvard, George Whitesides, helped inspire this. And he made all of these beautiful creatures just building on the molding and casting you've already done. This was a student from How to Make who went on and he made this little module that makes it easy to program pneumatics for soft robotics. So it's not just the soft robot, this is a kit to make it easier to make soft robotics. And I believe I showed this before, but this was former students at other lab who made inflatable. So here's a whole robotic arm made out of soft materials just by varying air pressure in bladders within these arms. So you could experiment with soft robotics. Then for electronics, there's a number of ways you could extend it. One is, this is a pick and place in my lab to automate electronics assembly. There's a number of lower cost kind of DIY pick and places emerging. Using a pick and place to do short run electronics production is a new sort of skill. And then in the embedded programming class, I just briefly mentioned PLDs and FPGAs, and learning to program programmable logic is very different from microcontroller programming. So that would be fine. Then for embedded programming, this is a link to TensorFlow Lite that runs in microcontrollers. There's also TinyML. These are different enough from the coding I taught. I briefly mentioned this, but we really didn't do it. So learning to do machine learning in embedded systems is fine for this week. It needs to start with electronics that you've made and interfaced, but learning to run machine learning in embedded systems is different enough that's fine. Likewise, OpenCV, this is a link to platforms for embedded video. OpenCV is the standard framework for machine vision. And once again, I've only noted that, but implementing embedded machine vision is a new enough skill to be fine for this week. Food. This is a colleague who's been experimenting with printing food, extruding it. And in particular, they've done a lot of work to understand why you do that, what you can print to make food that you can't do any other way. So playing with food printing. This is a former Fab class student who got interested. Oh, his site is down. But he's experimented with using the range of our tools with food. So using molding, casting, printing, milling, laser cutting, but doing it safely with food to produce food. And not doing it as a parlor trick, but looking at the benefits of that. So you could experiment with food. Then a really interesting thing you could do this week is experiment with the materials themselves. So Materiome, which we've talked about before, and let's see. They have a really nice library where you can tour the ingredients in and the applications out. And so now for most of you, you've just used materials available in the lab. A really interesting thing you could do this week is look at how you use locally available resources like eggshells, coffee grounds, gels. And then from those locally available resources, you can produce materials. And then if you produce the material, then going through the existing machines is fine, but milling or laser cutting a material you produced is fine for this week. Another thing you could do is learn more about the material. So this was a while back, a student made a tensile tester that I showed you a stress strain curve. This is a machine to let you measure stress strain curves. And so you could, this week, the heart of it could be learning about the materials themselves And then this was a more recent project. This was augmenting a 3D printer so that I had mentioned this before. It measures the forces there's a load cell measuring the force on the extruder. It measures the rate materials coming through, the diameter of it. It's looking at it. And from doing that, you can learn how to print an unknown material. So instrumenting a machine to expand how the machine works, to expand the materials you can use with it. So that would be descending into the materials. Then there's the universe of biotech. So DIY Bio is an organization of do-it-yourself biology. iGEM is a program with huge participation that links generally universities to do crash experiences in synthetic biology. How to Grow Almost Anything is a class at MIT that grew out of and links back to the Bio Academy, which is an academy class where you learn biotechnology. So it's a challenge to do a complete unit in biotechnology in a week, but there's subsets you can do. And so if your Fab lab has a sister lab, if you have access to a bio lab, there are a number of different processes you can do in biotech this week. Then this is a recitation on fiber processing. So there's weaving, knitting, crocheting, sewing, embroidering, are all processes you can do with fiber. This is a nice tour through automation of how machine knitting processes work. First, this was an early thesis of one of my students helping to introduce electronic textiles. So he showed how to sew circuitry to make functional clothing. And the embroidery machines, the software is fairly annoying, but PE Embroider and Ink Stitch are open embroidery frameworks. So if you have access to an embroidery machine, learning to program that is fine for this week. And then another sister class is Fab Academy to learn about textile technology. And the range of skills they cover fit for this week. And so these are all options to work with textiles. And so any one of these involves computer design and manufacturing. It's something we haven't covered. And so this is a broad tour I just did. It doesn't restrict the universe. You don't have to do one of these. You can use anything that meets these standards, but this gives you a feeling for the options for Wildcard Week. And what's fun is seeing the range of what people accomplish. So that's breadth. Now for the rest of class, I'm going to descend in on composites. I'd say the laser cutter is the most overused tool in a fab lab. The vinyl cutter is the most underused tool. And I'd say composites is the most underused process. Composites let you make large, light, strong things with complex shapes. And it's accessible in fab labs, but not widely deployed. So here are examples. Composites involve fibers and a matrix. And I'll talk much more about that. So in this first row, this is machining rigid building insulation foam. Then going through the steps I'm going to describe to make composite tooling. And then what you see here actually was a pair of blue jeans. This was clothing. It was squished in the mold with resin infused, and this made a hard shell case for a laptop. This is a bike frame. So this starts as a cardboard frame. Then instead of an exterior mold, and I'll go through this, this is an interior form that you form the composite around and take it out. And the cardboard form is still inside. And here now is the bike frame. This is machining a form that you form the composite around, and that makes these paddles. And then this is a beautiful example of making a whole kayak. This is a boat and then a kayak. And so this is laying up a composite skin. And this kayak, believe it or not, was done as homework in the class. Yeah, I'm going to go. Yeah, Adrian put this in the chat. I'm going to go through this in more detail. And I see, let's see, in the chat, Hank has an example of TinyML on the shelf. So these are all examples of what you can do with composite production. And again, in the past, we had everybody do this. I want everybody to be aware of it, and it's an option for this week. So what are composites? At the limit, so 787, so the 787 was Boeing's airplane made out of composites. And so the whole thing, this is how the airplane is made. It's made, and I'll talk more about this process. There's this giant machine that winds fiber with resin, and that makes the barrel of the airplane at the state of the art. So my shirt is strong in tension. I'm not strong enough to pull the fibers apart, but they fold easily. It's useless in compression, but it's great in tension. There are a number of materials that are the opposite. So epoxy resins, concrete, that are really strong. You can't compress them, but in tension, they either crack or they flow. And so the idea of composites is you combine those. So you have fibers that handle the tension load in a matrix that handles the compression load. So the 787 and the Airbus A350 are epoxy with carbon fiber. A really important historical composite that's all around you is concrete with rebar. That if you just pour concrete, like roughly the hydrostone or drystone you use, under tension, it would just crack and the cracks would propagate. And so universally, you use rebar with the concrete, and the rebar handles the tension and the concrete handles the compression. Fiberglass is glass with a matrix. The circuit boards you're using are composites. So FR4 is glass epoxy. FR1 is materials like paper or cotton in a phenolic. Garolite is basically the PCB stock. Automobile tires are composites. They're belts and rubber. Adobe is an ancient composite. Adobe, not Adobe, the software company, but Adobe, let's see, Adobe construction involves clay with natural fiber reinforcing. Paper mache is composite. And the most important composite of all is wood itself. What makes trees stand up is the wood fibers in the resin matrix together makes a composite. So all of those are examples of composites. Now, for you to make a composite, you have to pick the fiber and the matrix. So you can get the fiber in many forms. You can get chopped fiber that are short segments. And chopped fiber doesn't, it's convenient, but they don't make particularly good composites. So it's short segments of fiber, and then you put them in the matrix, and there isn't good force exchange between them. So if you're making a mold and you put in chopped fibers, it'll have better mechanical properties than not having the chopped fibers, but it's not nearly as good as continuous. You can have individual filaments that you wind. You can have composite tapes, and that was going on in the machine that makes the barrel. And then one of the most convenient ways is to start with fabric. So you start with continuous sheets of any of these fibers. You cut the fabric to size, and then you lay up the composite. Yeah, so yeah, Ricardo noting is they're convenient. They're better than not continuous, but mechanically they're not. For things like airplanes, for state-of-the-art composites, it's essential to have continuous fibers. So glass is a common fiber source, and carbon is a common fiber source. Also, you can use aramid or Kevlar. We don't routinely use these in fab labs. Down below, I'll talk about safety. Carbon fiber has the best structural properties, but it's very hazardous to use in a number of ways, and I'll talk about that with safety. Instead, what we like to use are natural fibers. So cotton, silk, bamboo, wood, linen, burlap, all of these come from sustainable sources. They're environmentally friendly. They're not remotely hazardous to be around, and they have good properties. In fact, I'm going to grab something up here. I'll be back in a moment. I happen to have next to me here, this is a sample of a natural fiber fabric composite in a matrix. So, it hurts if I hit myself on the head on it. I can't bend it. This is fabric in a matrix as an example of a natural fiber composite. I wouldn't make a jumbo jet out of that, but anything short of the stiffest, strongest, lightest materials, you can make really nice composites with these natural fibers. Then to make the matrix, there's a number of options for that. Most common is epoxy, but just conventional epoxy isn't environmentally friendly. And yeah, I'll talk about the coupon test shortly. Traditional epoxy is not environmentally friendly, also needs really good ventilation. Phenolics are used, urethanes, cement in cement composites. But again, there's a lot of work on natural resins. So, and I'll show you when I get to vendors, natural sources of environmentally friendly resins. And then something that's next door to composites is laminates. So traditionally in skateboard making, like I'm describing, you can start from fabric and lay it up. But what's common is you start with laminates, which are thin plies of wood, which are itself a composite. And then you heat and squish those and laminate the laminates. So rather than starting from fabric, you start from wooden plies and lay them up is a common way to make skateboards. So to source all of these, McMaster-Carr will sell, let's see, they'll sell Garolite, glass fiber, carbon fiber, and epoxy. I've shown these before, but the boat builders all use these materials to make boats. Fiberglass supply is not just fiberglass. This is a general composite production vendor that has all of these materials. Similar with Jamestown, CST is a composite focused vendor that sells all the materials I just described, specific for composites. Then some interesting ones are Lynn Grove has a wood composite that you can use as a source material. And Entropy Resins is one of our favorite vendors. This is proprietary, not open. My understanding is a core ingredient is reduced from sawdust. It's not 100% bio-based, but it's significant bio-based. And so they have this high bio content, low volatility, much friendlier epoxy. That's a nice choice for casting friendly fibers to make fiber composites. Smooth On that we've used for molding and casting makes a number of resins. And then here we get up to then, these are the vendors that make the state-of-the-art composites that these go into when you make things like giant wind turbine blades or production airplanes. These aren't designed to sell to you as individuals, but those are the vendors for state-of-the-art. So starting with something like, say, linen fabric, and then super sap from Entropy Resins, now you have the fabric for your composite and the resin, and now you need to turn it into the form. So one of the key concepts is the plies in the composite. So if I make a single sheet of the fabric, even if I have resin around that, it just doesn't do anything. It's squishy. It's not useful. The key to understand why I can't bend this is if we take, actually, let me make an arc. So if I have multiple plies of the composite, so what I'm drawing is, this is the fabric, and then in between the fabric is the resin that's holding it together. If I'm now trying to bend it, there's a radius of curvature. So if I try to bend it, what I'm doing is, if I'm trying to bend it down like that, the fiber on the top surface is in tension. And I can't bend this because to bend it, I would need to stretch the fibers on the top, and I can't do that. So for a composite to work as a composite in the way I'm describing, you need some thickness that has multiple plies, and you need a gap between the top and the bottom surface to have the radius of curvature for the fibers to be in tension. So to make a composite, you need to lay up plies. Now, if you look at this diagram, what you'll see is, if I bend it the other way, the fibers on the bottom are in tension. If I bend it this way, the fibers on top. All of this material in between actually isn't doing much for me. So what's common is in composite to have a core. And so the core you can use to reduce mass. So the composite core let's see, looking at the chat, Hank has a link in the chat. You can use aluminum honeycombs, you can use hollow forms, you can use foams. Let's see, I think I'll talk about there's a whole community that makes cardboard surfboards, where you make a cardboard form, you lay up the composite around it, and it just stays inside. And so this hollow form is both what you're using to make the form, and then you're reducing the mass to make the composite lighter. You don't need mass in the middle. It's the top and bottom surface that are load bearing. So it's typical to have cores in your composite. Then just spars and ribs there's a hierarchical structure. So when you make an airplane, typically instead of a single composite, you have a load-bearing beam, and then you hang off of that these load-bearing forms. And so it's sort of like the construction of a tree. You have a hierarchical tree of how you distribute the load through the structure. And many years ago, my lab helped introduce the idea of what we call digital composites, where in the way I'm describing, let's see if we go back to 787 composite. I visited the factory where this machine is. This is a machine that lays up the composite that's the size of the airplane. So done that way, to have continuous fibers spanning the airplane, you need a tool the size of the airplane to make it. And then you also need, and I'll talk about this in a moment, to cure it, you need an autoclave. And the autoclave is an oven the size of the airplane to heat it and pull the vacuum I'll talk about. So in this project, what we studied was, instead of one big composite, we make little composites. And in fact, we're doing this very carefully. We're making loops of carbon fiber, but then we link them in structures like Lego. But these are carefully designed to transfer forces so that we make a volume out of the composite, but we don't need we have a small tool that makes these parts, and then we assemble those into big structures. And we went on to show, and these are things I think I've shown before. By changing the shape of the parts, you can tune, this is rigid, this flexes. This is what's called auxetic. So when you push it, the whole thing shrinks. This is what's called chiral. So when you push it, it twists. And we use those sort of parts to make, this is a test airplane that instead of a big tool is made out of assembling lots of little parts. And so these are discretely assembled digital composites. Okay, so you've picked a fiber, you've picked a matrix for it, you've designed your composite. Now, how do you make it? So the first note is, this is a design tool to design the composite. If you think about, let's say you wanted to make that helmet, if we look at this image, if you just take a flat sheet of fabric and drape it over the helmet, it'll have wrinkles. So what you do is you make cuts in it, and the cuts are such that with those cuts, when you lay the structure up, they all line up and you get a smooth, continuous structure. And so there's software to help you design that. But one of the ways you can do this is if you design a mold for your composite, for the helmet. So this picks right up from the molding and casting class. If you lay the fabric that's going to be made for the composite in the mold, you'll see where it bunches up, where it doesn't lay flat. And then you can make darts. You can make cuts that remove the material where it bunches. So then it lays flat in the mold. And in fact, you can see that if we go back to it in this briefcase, if he hadn't done that, you'd see ripples at the corner, but he laid the fabric in it, he cut it and made little wedges so it all fits together so you get clean seams. So one part of the process is assuming you're starting from fabric, given that you're making a curving shape, you need to figure out how to cut the fabric so it lays smoothly in your mold. And now we come to the heart of the process. So this is a series of tests my lab has done over the years on composites. This is a series of side views. And so if we look from the side, so let's see, I'm laying up sheets of fabric. Then I'm putting in the resin. If we look at the side view, I see the threads. And now what I want to do is I want to squish it. And the reason I want to squish it is most of the work is being done by the fibers, not the resin. And so ideally, I want the fibers roughly as close to together as the size of the fibers. So let's see. Okay, yeah, another image from Adrian. So a beginner composite might be 50-50 fiber and resin. A state-of-the-art composite is about 90% fiber, only 10% resin. And so what you need to do is you need to force the resin into the fabric, and then you need to get rid of the excess. And what these images are showing are what the composite looks like with a number of different ways to produce it. And you see, as we go from here down to here, the fibers are getting closer and closer together. And the closer the fibers get together, the better the composite is for the stiffness relative to the weight, which is called specific stiffness. So how do you do that? A crude way to do that that's useful to start is if you make your mold, lay up your composite, if you just fill a trash bag with water, you can use water from the tap in a trash bag as a mass. And that's 0.036 pounds per cubic inch. So that's easy to do, but it's not a lot of force. More common is if you lay up your composite, if you put the whole thing in a bag where you pull a vacuum, so you take all the air out. If you take the air out, then we have the air mass going from you up to the top of the atmosphere. And air doesn't feel heavy, but if we take the whole atmosphere on top of us, that's 14 pounds per square inch. And so this was 0.036 pounds per cubic inch, but to go from 0.03 to 14, that's 1, 2, 3 digits, you need 100 inches of water to add the weight of air. So we have this handy supply of force above us in the air mass. So you pull a vacuum and you use the weight of the atmosphere to do the compaction. And then what's actually the best way of all is if you clamp it. So if you take just a bar clamp, a humble bar clamp like this, if you have your mold, you have the materials, and then you have a board on top and bottom of your mold, and then you have a bar clamp on the sides. By compressing the bar clamp, you can easily get 100 to 1,000 pounds per square inch. You can get tremendous forces. The limitation on that is if your mold is really big, like say you're making a jumbo jet, the bar clamp here doesn't get a lot of force in the middle. What's good about vacuum is everywhere. So you need to use vacuum mold if you want good compaction over a large area. If you want to make a really good composite, but it's not huge, you can use a clamp. And if you want to make an okay composite, and in fact, this example I have here is only okay. This isn't great compaction, but it's still stronger than I can bend. You can do that just by putting weights on it. But in any case, you have to infuse the resin, and then you have to drive out the excess. Now, this term I've been using, coupons. A coupon is a test composite. And this was a series of tests we did of different materials. But a coupon is you make a strip out of the composite and you use it to test the process. And so when you're learning about composites, before you spend a lot of time with your mold, start by making just simple rectangular strips to test your fiber and your compaction. And what came out of these tests, for example, is we found how good linen is compared to, we compared a number of different materials, and it showed that linen has surprisingly good properties to make friendly composites. And this is linked to analyzing, using one of those material testers I showed you before, lots of different materials. So if you're going to start composites, make little test coupons. Now, there's still a whole tree of decisions. So an open mold, which was more common traditionally, is you make one side, you make a mold that's one side, you lay in your composite and resin, and then we're going to have a top layer and pull the vacuum. So now this surface has a really good finish that matches the mold. The backside doesn't have a good finish. Compare that to a closed mold is you make a mold for one side, and then we're going to make a matching mold for the other side. We lay in our fabric and resin, and then we compress the two-sided mold. The one-sided mold needs you to pull the vacuum. The closed mold, which is a two-sided mold, eliminates the need for the vacuum and can let you get larger forces than vacuum. And so increasingly, composite production has moved from open to closed molds. Okay, then we need to get the resin in. So what the easiest way to do this is a wet layup. And I think Sam has, yeah, good. So here's Sam who made that, and Tom's his helper. And he's going to show the steps. So first step is he's machining the form. And remember, the mold can be outside squishing in, or the mold can go on the inside as a core that you form around. So in this case, he's making these paddles, so they'll be the inside. So here he's machining the form. Okay, now it helps to have a helper for this. Sam and Tom, this goes pretty quickly. So Sam and Tom are mixing the resin. They've already cut the fabric to size. So what you see, see, I want that to go away, is these are sheets of the fabric cut to the final size. And they're going to do wet layup, meaning they're going to spread the resin and squish it into the fabric. So here they are spreading the resin in the fabric, then taking each ply of the resin-infused fabric and laying them up. And you see those the skinny ones are because he wants some stiffeners where it joins the body of the paddle. So he wants it a little thicker there. Okay, now he's laying them up into position around the forms. So that now that's called wet layup because it's exactly what it sounds like. It's a wet layup. And now in this case, he's going to vacuum bag it to do the compaction. So there's the vacuum bag, and I'll talk about that in a moment, what's actually inside the bag. He pulls the vacuum, and then it's now squishing down and it's driving the resin out. And now he's got these high-performance composite paddles done. So that's an example of wet layup. Joaquin is asking a question in the chat about reverse engineering. Can you scan and print? Joaquin, reverse engineering would be fine for this week as long as you close the loop. So scan, print, and then measure what you print to measure the deviation. As long as you characterize the process, that's fine for this week. So that's wet layup. Pre-preg, which used to be common, is where you buy the fabric with the resin in it. And to prevent it from curing, typically it's refrigerated. So you need to keep it cold. That's a nuisance. And then in industry, most common is RTM and VARTM. So RTM is resin transfer molding. And that's where under a lot of pressure, you force resin into the mold. And VARTM is vacuum-assisted resin transfer molding, where you pull a vacuum on one side to pull it out, and you push in from the other side, and that pumps the resin in the mold. And so compression molding is where you have a clamp. Inflation, this is how bike frames are made. In a when you make a bicycle frame, typically it's done by inflating it from the inside into the mold to make the form. And then vacuum bagging, let's see, a crude way to do it is, that works surprisingly well, is these are vacuum bags just designed to shrink clothing down. But you can use these as simple vacuum bags for composite vacuum bagging. And now this is a link to West Systems. Oh no. Let's see. The let's see if they move that and I can find it. Oh, good. Okay, so they just moved the link for it. I'll have to fix that link. So this is a nice app note that describes all the steps. And in particular, there's a figure I really like here. This shows what was going on in that video. So you have the mold. This shows it flat, but almost never is it flat. There's usually shape to it. We might be making a part of a car body, a bicycle helmet, a briefcase. You have your laminate. Okay. Then after the laminate, there's what's called a bleeder and a breather. So when Sam did his layup, if we go back to that, right here, you see those dots. What's going on there is we have this bleeder layer and the breather layer. And if we take this example, if there's, let's see, so I'll make a mold. And again, I'm just drawing an arbitrary mold, but think a skateboard, a bicycle helmet. If I lay up my plies, I infuse with resin, I then compress it. If the mold isn't very large, what I can do is I can squish the epoxy out the sides, the resin. So in resin transfer molding, you actually force the resin through the mold. In a kind of beginner resin transfer molding, what you do is you squish from the top, and then the excess resin migrates through and goes out to the sides. And if the mold isn't too large and the force is large, you can do a good job with that. The problem with that, again, is if you have a really big mold, like say you're making an airplane, it's hard to get the excess resin all the way out to the sides. So then what's happening is you have your plies in the mold. Then you have a sheet that has holes in it, a bleeder, and then you have a breather. And the breather is, think of like soft cotton. And what that's doing is when you pull the vacuum, if you pull the vacuum right away, there's nowhere for the excess resin to go. But if you have the bleeder and then the breather, the resin goes through the holes in the bleeder and then gets absorbed in the breather. And that's what's happening in this image down here. That this is the excess resin going from the layup through the bleeder to the breather. And so these are the steps in laying up. And then finally, outside the breather, you have the vacuum bag. And I showed you can buy a preset vacuum bag. And then commonly, you just have a polymer sheet, and then you have a sealant, a kind of a sticky, dense clay that you can use to just stick it together that withstands the vacuum. And so a common skill, and that this shows all those steps, is to make vacuum bags. I would say, though, especially for kind of Fab Lab scale composite, there's a lot of vacuum bagging that can be done with compression molding. Compression molding is where you just clamp it. Compression molding eliminates the need for the vacuum bag and can actually give you better compaction, which means a better composite than vacuum bagging. So after that is an autoclave. One of these giant tools is heating it to help cure it, but it's putting on an overpressure. So you can actually go beyond atmospheric pressure and have even greater pressure with an overpressure and autoclave. And then two final notes. Let's see, pultrusion is if you wanted to make a continuous composite part. Pultrusion is where you do all the steps I described on the fly and you pull a composite out. And so that makes things like composite beams or pipes. Once you're done all of that, typically the edge of the composite is rough. So you need to trim the edge, and that matters for safety, I'll talk about. And then typically when it comes out of the mold, the surface of the composite is a bit rough. And so a common final step is a clear coat. When you look at, say, a composite bicycle that has or a composite car, if you've ever seen one, it has a smooth, shiny surface. It doesn't come out of the mold with the smooth, shiny surface. Clear coating is a final step where you fill in the irregularities using, again, the molding and casting materials. So to make the mold, most commonly you machine it. So this was an example of one of my students, and he actually made a smart mold. So he's machining the mold, but what he's actually doing is he's casting into the mold both heaters and temperature sensors. And then around this mold, here's a beautiful carbon fiber epoxy part he laid up. And in fact, you can see the darts in the part is that little line there. So most common is machining the mold. You can fold a mold. This was an example of cutting and folding a mold to make a part. And then, okay, good. I do link here. Is skinning. So actually, let me do a better link for that. This is what I had showed before, but now to show it again. And what's going here in this process is you actually just use cardboard to make the shape of the surfboard. And then you skin that to make a continuous skin layer. And then around the skin layer, you lay up the composite. And with that, you make these beautiful cardboard surfboards. They're funny looking. It looks like cardboard, but they're stiff, light, strong, high performance. Yeah, see, this is showing skinning it before the composite layup. Now, safety is a really important concern for working with composites. So the reason we stay away from both glass fiber and carbon fiber is a sheet of from a number of vendors, you can buy carbon fiber fabric that looks like that. In that form, it's fairly harmless. You see the person holding gloves, but it's fairly harmless. Same thing for glass fiber. The problem is if you do anything with it, if you sand it, machine it, cut it, any process like that, you release short fibers. And the short fibers from composites are, so asbestos has been forbidden around the world for the lung disease it causes. And that's exactly what this does. If you breathe these fibers, they get in your lungs and they don't leave, and they can cause lung disease. Short of that, let's see, if you okay, you'll see over and over, like, I've got a carbon fiber rush. What do I do? you'll see, you know, all of these, somebody posting these pleas, and it's kind of hopeless. If you get these fibers in your skin, they get embedded, they cause serious irritation, and there's no easy way to get them out. So compared to that, the natural fibers degrade naturally biologically. So it's fine to use glass fiber or carbon fiber if you just cut it with scissors, and it's fine if you don't do any further processing. But anything like drilling, machining, sanding, any of those operations turn them into very hazardous materials. To work with them, to sand carbon fiber, you need really these heavy duty respirators. And this is for breathing. That much better is something that looks like that protects your eyes. You know, so this is what you need to work with carbon fiber or epoxy safely. So that's why we steer you away from them. Then even if you're using natural fibers and natural resins, so first, the serious epoxies need really good ventilation. These are fairly large sections. The friendlier ones don't need as serious, but you still need to use them in good ventilation. But they're sticky and messy. It's like molding and casting on a large scale. So you want to protect your eyes from things splashing in. You want to protect your clothing. You want to wear gloves. You want to protect your workspace. All the things I said in molding and casting, with this extra addition that if you're using carbon fiber or glass, it also becomes hazardous if you process it. And finally, the same molding and casting, if you're making reasonably large sections of composites, there's an exotherm, and you need to worry about temperature regulation. And so even if you don't use a trash bag of water to compress it, you can use it just as a thermal mass to help take the exotherm out. So if you're going to do this assignment as a group, produce test coupons, individually review the safety data sheets, and then make a mold like we did in molding and casting. But it can be in a lighter material like the building foam. And then you skin the mold and do layup and produce a composite part in it. So it used to be we had everybody do this assignment, and this was one of my favorites. We dropped it because of all these other topics, but it's still a good option for this week. I'd like to see more labs being comfortable with working with these environmentally friendly composites. So stepping back, we're fairly forgiving. The one thing we don't want to see this week is just a better version of an assignment you already did. And we don't want something that's just simply a craft skill. We want to involve design tools and a way that you can transfer it so that somebody else can reproduce your work. Other than that, any of these options are fine. And the goal really is not for everybody to do the same thing, but for everybody to do a different thing and use this to see the range of techniques that are possible in your lab. And so that's Wildcard Week. As usual, open time, and there's only a few of those left. Make good use of them. We have the wonderful all-in group talking about who gets access to labs, how you reach your community, how you have impact. And that's gone from a recitation to a working group to a class, and we'll have some presentations from the class. And then after this, we're done with new technical topics. This class is going to be on how systems fail and how you design the integration. And then I'll talk about implications, applications, IP, and then we're up to final projects. So please make sure you're working in a tracking project. Please get going on your global review to leave time for global to local and local to global. And please make a schedule for the remaining weeks to figure out how we can get you through them. If you miss that, you don't fail, you just go into continuing, but we want to get as many of you through as possible as we can. Okay, happy Wildcard. I look forward to seeing what you do with that. So Adrian and crew will see you on Saturday. I'll see you at the Monday recitation, and then see your wildcards next Wednesday. Bye-bye.
Okay.
Bye.
Bye.
Last class, 10
Adios,
minutes.
adios.
Ciao, ciao.
Ой, mochi was queen,